Okay, hello everyone. Today we have our speaker, Nick Ballering from University of Virginia. So before I introduce Nick, I would like to let you know that you can, if you have during the talk, if you have a question, please write your clarification and urgent question in chat. Then one of us will read the chat and ask question to the speaker. And please hold the longer questions to the end. You can either use a chat, or you can just raise your hand. You can ask question directly. So now let me introduce Nick. Nick did a PhD here at University of Arizona with George Rickey. And then he stayed here as a postdoc and worked with Josh. And now Nick is Origins Fellow at University of Virginia. And you're going to talk about exciting work on one of these new work, right? Is simulating observations of protoplanetary disk ices. Okay, Nick, the floor is yours.
Okay. Thank you, Serena, for the introduction. Thank you for the organizers for inviting me. As Serena said, I'm a VICO Fellow, which stands for the Virginia Initiative of Cosmic Origins. So it seems fitting that I'm presenting at the Origins seminar here. So today I'll be talking about some work on simulating observations of protoplanetary disk ices. This is work I've done with Ilsecleves and Dana Anderson, also here at University of Virginia. So in this cartoon, I show the major steps in the star formation and planet formation process, which I think many of you are familiar with. We start out with a molecular cloud where dense cores collapse into protostars surrounded by an infalling envelope and an accretion disk. Eventually, the envelope dissipates and we're left with a young star surrounded by a protoplanetary disk where we think a lot of the planet formation process takes place. And then eventually this disk dissipates and we're left with a mature planetary system. So what do we know so far about the ices in these various environments? So molecular clouds, we can study the ices in them by looking at background stars and studying the absorption spectrum through the clouds. So some of this work was done already back in the 70s and 80s. This is a spectrum that's probing the 3-micron absorption feature from water ice through various lines of sight in the Taurus molecular cloud. This work took off a lot more with Spitzer, of course, and here's some work from Spitzer showing an absorption spectrum through a dense cloud, a dense core, again in Taurus, and detecting again the 3-micron feature from water ice, as well as CO2 ice at 15 microns, methanol ice around 9 microns, some other features which are around 6 to 8 microns, which might be from things like NH4+. And eventually there's been enough statistics on molecular cloud ices that we can make plots like this, where the ice column density can be seen to correlate with the visual extinction of the given sightline through the cloud, and those correlations look different for different species. Moving on to the protostellar phase, these show very rich ice absorption spectrum. In this case, the ice is coming from the surrounding envelope of material. And again, some of this original work was done back in the 70s and 80s. One of the earliest ice detections was from the envelope around HL tau, again, with the broad and deep water ice feature at 3 microns, which is accessible from the ground. I believe this work was actually done from Mount Lemmon. And of course, Spitzer took it up a notch, seeing many, many features towards protostars, CO2 ice, methanol ice, CO ice, water, of course, ammonia, methane. So this is a brighter, more massive protostar. This is more of a low mass protostar. And again, there's been enough statistics done on these to make plots like this, where we can look at the distribution of abundances of some of the most prominent ice species towards low and high mass protostars. Skipping ahead to mature planetary systems like our solar system, the ices are pretty much locked up in comets. And so comet observations can get at the icy reservoir in our solar system. And again, most of this is done through comets that are outgassing, although we've recently actually sent the Rosetta space mission to a comet to observe it more directly. But again, enough comets have been observed that we can look at, take a statistical look at the abundances of some of the most common species. So, CO has been detected in more than 10 comets, CO2 in more than 10 comets, and this shows the distribution of their ice abundances relative to water. And even this graph is 10 years old now and doesn't include a lot of the newer work, including the results from Rosetta. So you notice that I skipped over the class 2 disks for now, and that's because the class 2 disks have much more limited ice detections. And so we haven't yet had the data to build up those type of statistics. And so there are three sort of techniques that you can use to study ice in class 2 disks. The first is absorption, again, through disks that happen to be edge-on. And the way this works is instead of using a background star like we do for the molecular clouds, you use the disk itself. So you look at the thermal emission in the infrared from the star and from the inner hot parts of the disk. That radiation is then scattered from somewhere near the surface of the disk. That scattered light then passes outwards through the edge-on disk, through the colder outer material where the ices are, and the absorption of the ice is imprinted onto the spectra as it moves towards the observer. And what this creates, if you image a disk in the optical or the near infrared, is this sort of bilobed emission pattern where you've got bright light from above and below the denser midplane, and that's coming from scattering. So you're looking at that scattered light and seeing the imprinted ice features. And so this is tricky to do. The 3 micron feature is the easiest to observe, of course, and it's been done through a handful of disks from ground-based facilities. But beyond water, we know very little about ices in class 2 disks. One source where we have seen ice beyond water is HK Tau, which has a CO2 detection from the Akari satellite. And there's this other disk that has a nice Spitzer spectrum, although this one is a little bit confused with potentially some foreground material that's not part of the disk. So there's a little bit of questions involving which of these features truly come from the disk. And both of these were possible because they're sort of on the very brightest end of what we can see from disks. Most, these are the mid-infrared here is, hundreds of millijanskys, where a typical sort of edge-on disk has an infrared brightness of maybe a few millijanskys or less. So that's really the holdup, is just we need more spectral sensitivity in the infrared. The second way to get at ice abundances in disks is to look for their features in scattered light. And this has been done for even fewer disks. What you do here is you have to try to isolate the scattered light from the surface of the disk and get measurements of its brightness both in the ice band, so at 3 microns, for instance, and then outside of it, and use sort of make a coarse spectrum at various apertures of these images, and you can see the absorption feature here at 3 microns. So this has been done for 2 or 3 disks. And the third technique is to look for far IR emission features. These are only available for water. So the prominent features here are at 43 microns and 63 microns. And this has been done again for a few disks, first with the ISO observatory, and then later on a bit with the PAX spectrometer on Herschel. And here's a couple of examples of that. So, we don't have that much data, but what's the motivation for getting ices in these disks? Well, first of all, disks are complicated beasts, right? If you look at this schematic on the right-hand side, you can see that there's a lot of variation in their properties, both radially and vertically. There's different layers with different constituencies, and there's lots of processes going on, different heating and cooling, mixing. And so we want as many tracers as we can to try to understand these things. On the left, you can see how that sort of plays out. There's the near infrared probes parts of the disk, ALMA probes different parts of the disk, gas and dust probe different parts of the disk. So by adding in ice as an observational tracer, it's one more tool in our toolbox for understanding disks. Ices also play a very critical role in the pebble accretion scenario of planet formation. They make the dust grains stickier, which facilitates their growth through collisions. It also facilitates planetesimal formation as these icy pebbles drift inwards when they encounter a snow line. They can create a concentration of solid material that can enhance the processes of planetesimal formation. In terms of comparing to measurements of comets, if we measure the ices and disks, that's the most direct way to make that comparison, more so than protostellar ices, which primarily probe the envelope, or gases and disks, because it is the disk ices that are directly leading to comet formation. And lastly, ices are very important for storing and subsequently delivering biocritical volatiles to potentially habitable terrestrial planets. So fortunately, I think our ignorance about disk ices is going to come to an end. There are a number of new observing facilities that are poised to revolutionize our view of disk ices. First and foremost is JWST, which will cover the 1 to 28 micron region, which spans all of the major ice features that can be seen in absorption. Has plenty of spectral resolution available, unprecedented sensitivity, which we saw was very important especially for the edge-on disks. High spatial resolution, which will be great for isolating disks from a surrounding material, as well as IFU capabilities that could potentially map the ice features. There's also a mission called SPHEREx, which will probe the ice features out to 5 microns. It'll have a slightly lower sensitivity, spectral resolution, and poorer angular resolution than JWST, of course, but it will be an all-sky survey, so hopefully we'll discover a lot more ice features and disks that JWST doesn't get to. In terms of the far IR emission features, SOFIA just released their sort of instrument roadmap where they're trying to go with their instrument facilities. And one of the concepts for their, quote, step 2 instrument development would be a far IR spectrometer from 25 to 122 microns that would cover those far IR water ice emission features. And lastly, OST is one of the future planned, potentially planned flagship missions. And it'll, again, be very sensitive to those far IR emission features. OST stands for the Origin Space Telescope. So that is the third use of origins in a proper noun this afternoon. So what we do is we, in this project, wanted to simulate observations of protoplanetary disk ices to complement these upcoming measurements. So we wanted to have these models available to, one, prepare for prepare observing programs with these instruments and formulate testable hypotheses. 2, to have these models available to interpret data when the data become available and connect the measurements back to fundamental disk properties. And 3, to guide design specifications for future observational facilities that could target ices. So below is the flow chart for how we actually put together these models. I'm going to go through a few of these steps in a bit more detail next, but I'll give you a brief overview of our methodology. In short, we have 2 main steps. 1, we run a chemical evolution model that derives the abundance and the distribution of ices throughout the disk. And 2, we use the results of that to put into a radiative transfer model and simulate the observable spectral features. So going through the methodology in a bit more detail, we first set up the disk model. And in this case, we modeled it sort of a typical class 2 T-Tauri disk. So we had to fix the inner and outer edge. We set a flared vertical structure. We used 2 different populations of dust grains, a small grain population that traces the full vertical extent of the disk and a larger population of dust grains that's more vertically settled towards the midplane. This is all sort of a fairly standard way of setting up the disk model. Then we compute the temperature and radiation field throughout the disk, which are required ingredients for the chemical model. The chemical model itself is based originally on the work of Fogel from 2011. It's a kinetics-based model, so it uses known chemical reactions with rate coefficients, and it evolves the abundances forward in time based on those reaction database. It's a 1 plus 1D model, so it's calculated in both radial and vertical directions. The reaction network that we use for this work had 654 total species and 7,039 different reactions. We set it up in two different ways for the initial chemical conditions. One chemical model was sort of an inheritance-based model, and by that we mean we used all of the molecular abundances as they're measured in protostellar envelopes. So assuming that the disk directly inherited its molecular makeup from the protostellar phase. And the second model was an absolute reset scenario where we put in only atomic species, but we preserved the same overall elemental abundances as in the inheritance case, with the exception of H2, which we left not in atomic form, but in, or hydrogen in not in atomic form, but in the form of H2. So then after the chemical model is run, we extract the ice distribution for 6 key species of interest that were then put into the radiative transfer model. So we selected water, CO, CO2, methanol, CH4, and ammonia. And we extracted their distributions at 4 different time steps in the disk's evolution. So then we have at every point in the disk the amount of dust and the amount of each of these 6 ice species. And so that's what we need to specify what is the opacity at every point in the disk. However, based on the number of cells in the model, specifying into the radiative transfer code a unique opacity mixture at every point was impractical. For one, you'd have to compute the opacity many, many times for these, for all the variety of different ice and dust mixtures. And furthermore, the way that RADMC, the radiative transfer code works is that for every opacity mixture that you want to use, you first specify the opacity, and then you have to specify for that opacity the distribution of mass throughout the disk for that opacity. So that would be highly impractical. So what we did is try to reduce the problem by grouping model cells with similar ice and dust volume fractions using a k-means cluster finding algorithm. And I'll try to show you a little bit more about what I mean by that in this figure. So again, at every point in the model, we know the volume fraction of the 6 ice species of interest as well as the dust. And what we're showing here, and so that occupies sort of the 7-dimensional parameter space. And here I'm showing different projections of that parameter space. And for instance, if you look here, you can see every point in this panel is one cell from the chemical model. And on the y-axis is its methanol volume fraction, and on the y-axis is its water volume fraction. And so then we use the k-means cluster finding algorithm to sort of group these points together, where group points together that have similar overall ice and dust mixtures. And that lets us reduce the problem from having hundreds of different opacities that we need to compute to having in this case, 25, although actually it's double this because we do this process both for the small grain population and for the large grain population. So that's a trick we use to simplify the radiative transfer problem. This is where those sort of grouped zones actually fall within the structure of the disk. So here on the y-axis is the vertical coordinate of the disk, and on the y-axis is or the x-axis is the radial coordinate of the disk. And you can see here the different symbols correspond to which of those groupings, which of those zones that point in the chemical model was assigned to. So this zone 1, all these little pluses are regions at small radii and high vertical extents that are basically ice-free. And then you can see here the different layers throughout the disk where we've grouped them based on their ice mixture. So down here would be an ice mixture that is very rich in, for instance, CO. So then when we've simplified the problem, we then, for each of those zones, mix the optical constants of the constituent ice and dust species using the Brugmann mixing rule, and then use Mie theory to compute the opacity spectra and the scattering matrix. So here's just an example of what our opacity spectra look like in the end for 3 different zones. The dark blue line is for the zone that has got dust only, no ice. This darker blue line here has a lot of water in it. So you can see a prominent peak in the absorption opacity for the water at 3 microns, as you'd expect, and a dip here in the scattering opacity to generate the scattering spectral features. The sort of more cyan curve also has a lot of CO2, which you can see its features here and here. It's got CO, it's got some methane and some methanol. And then we take that, put it together in the radiative transfer code, and we generate a model image at each wavelength of interest. And then we can combine those model images to form model spectra. All right, so let's take a look at the results. First, what do we find from the chemical evolution code itself? So here I'm showing the distribution of water ice at 4 different time steps. Its distribution vertically and radially in the disk for both the inheritance chemical model and the reset chemical model. And so you can see the water is fairly broadly distributed vertically and radially throughout the disk. Methanol has a nice broad distribution in the inheritance model, but very, very low abundance, hardly seen in the reset model, which shows that methanol is really hard to make through disk chemistry alone. The CO2 is also fairly broadly distributed. It's interesting that it does show some time variation, especially in its upper and outer region of the disk, which we expect to be where our observations are most sensitive. So in the inheritance model, this is decreasing in this upper and outer region, or in the reset model, actually, it's pretty empty at earlier time steps, and actually the amount of CO2 ice sort of builds up at later times. Moving on to CO and methane are both much more concentrated towards the midplane. And so already we know that they're going to be harder to detect. And we can also see that the methane is significantly more abundant in the inheritance model, but in both the inheritance model and the reset model, the methane ice abundance tends to grow with time. So now let's take a look at how this translates into potentially observable spectra. What are the outputs of the radiative transfer? So first, let's take a look at the effect of these observable features from the inclination of the disk. So here I'm showing the sort of near and mid-IR region for 4 different disk inclinations, all close to edge-on, 75 degrees, 80 degrees, 85 degrees, and 90 degrees. You can see from what's labeled here that we can readily detect water ice, CO2 ice, both around 4 microns and at 15 microns, and methanol ice. And we're not able to easily see from these spectra any CO, ammonia, or methane. We can see as you go from lower to higher inclinations that the overall continuum gets much fainter, but that the features from the ices tend to get more prominent. There's also this thin gray line that I've overplotted here. This was a model I ran also at 90 degrees inclination, but with scattering turned off completely in the radiative transfer. And so what this shows is that all of this flux, sort of shortwards of 8 to 10 microns, was at some point scattered in the radiative transfer. And so all of this flux here is due to light that was first scattered and then passed out of the disk. And so what that means, and then at longer wavelengths, this continuum is due to sort of direct thermal emission. And so what that means is that the background radiation source that we're seeing these features through, it's very wavelength dependent. And so that's a very sort of a complicating factor in interpreting disk observations. It's one of the important reasons to use radiative transfer to interpret them. In terms of the far IR water ice emission features, we see that the features are much stronger at face-on disks. They get weaker as you go towards edge-on disks. So now let's take a look at the effect of the initial abundances and the subsequent evolution. So of the ices, the CO2 shows the strongest variation in its feature strength with time. You can see that both in the sort of feature around 4 microns and the feature around 15 microns. The blue curves are for the inheritance model. The orange curves are for the reset model. And in both, the time moves forward from sort of dark to light in color. So you can see that for the inheritance model, the feature starts out stronger and weakens with time. And the reverse is true for the reset model, where the feature starts out a little weaker and grows in time. And this was the same pattern we saw for how the ice abundance was changing in that upper and outer region of the abundance distribution from the chemical models. Again, suggesting that these types of observations are strongly probing that particular region of the disk. Also note that these tiny wiggles in the curves are just noise from the radiative transfer. They're not real features. Comparing what we see from the inheritance and reset models, as you may have guessed from what I showed earlier, the methanol shows the most striking difference between the two. So in the reset models, we see absolutely nothing from methanol, whereas in the inheritance model, we see a nice methanol feature that doesn't change too much with time. So looking for methanol ices would be a great discriminator between sort of a reset and an inheritance type chemical scenario. So those were for all spectra from spatially integrated disk spectra. But we can also, since we make our images, we make our, an image for every wavelength, we can also inspect what we would see from spatially resolved spectra of the disk. So again, here's an edge on disk, and I'm showing in the background what the disk looks like in scattered light. You can see this bilobed structure with emission from above and from below a midplane. Now we take our model, if we put different apertures at different heights in the disk and extract their spectra, this is what we find. A little bit higher up in the disk, this yellow curve, we can see pretty prominent water ice feature, as well as weak CO2 and methane features. If we move our aperture down a bit, a little bit closer to the midplane, the features get much more prominent. H2O gets more prominent, CO2, methanol. And if we put an aperture right at the midplane, we get this purple curve, which you can again see these strong features. In addition, we pick up features like CO, which we know exists closer to the midplane. So these features are seen in the model, although the overall continuum, if you were to try to extract a spectrum from the midplane, is a couple orders of magnitude fainter. So that would be very difficult to do likely in practice. And one of the motivations for doing this sort of analysis is that JWST will actually be able to carry out observations like this. The spectral modes of JWST, the near spec and near instruments have IFU capabilities. So if the disk is edge on and is being observed and it's large enough on the sky, you'll be able to pull out these types of features, hopefully, and get a more clear sense of the vertical structure of the ice distributions from those observations and be able to test these types of models in more detail. So now I'm looking at a face-on disk, and again, looking at the spatial variations of the ice features. And so now I'm plotting what you would see if you looked at a face-on disk with different sort of annular apertures. So this is an annular aperture, from 25 to 35 AU and going out towards the edge of the disk. And so if you look at the sort of near IR to mid IR features, you can see as you go out into the disk that the H2O feature, now seen in scattered light, again becomes detectable. And that, of course, has been observed, but we could also potentially observe CO2 features in scattered light. And if you go out to the very outer parts of the disk, perhaps even CO or maybe even methane features in scattered light. Doing the same thing for the far IR region. The feature strength over continuum doesn't change too much based on what sort of aperture of the disk you're looking at, although at the very outermost parts of the disk, the features do get a bit weaker. So as I showed, that these features sort of can be seen in these model spectrum by eye, but can they actually be observed with JWST in its given form? And so to test that, I took the model spectrum. Again, now we're back to the disk, sort of disk integrated spectrum. and I ran it through the JWST exposure time calculator. And the input model here is shown in this black line. And again, you can see the features we've been talking about: water, CO2, methanol. And the overall brightness here is about on par for a typical edge-on disk, right? A few millijanskis or fainter. These gray points here are what we get out after a couple hours of JWST integration time. These are what we'd expect for the data. And you can see down at the fainter part, you can actually see them. Where the disk gets brighter, they're pretty much hidden behind the black line. And then I take those points and I smooth them and to show the green line and what you would actually be able to recover from data if you took these gray points and smoothed them. And you can see the green line tracks the input model quite well. So I think the answer is yes. I think JWST will be more than capable of actually detecting these features. So they can detect the features, but will they? And again, I think the answer is yes. So I looked through what's sort of in the queue already just for cycle 1 of JWST, both from the ERS programs, the GEO programs, and the GTO programs. And I see, by my count, 13 edge-on disks that will be observed with either the near-spec IFU, the MIRI IFU, or both. So that's very encouraging. I think we're already on our way to expanding this field quite a bit. There's also an additional program that I wanted to highlight. This was one that I was involved with that was accepted. Ilsecleves was the PI of this project. And this is for a face-on disk. It is for the disk V4046 Sagittarii. This is fairly nearby at 72 parsecs. It's around a K-star binary, not perfectly edge-on, viewed at 33 degrees inclination. And what's unique about this disk is that it's quite big. And so if you look, here is a scattered light image from SPHERE. It's a bit saturated. And then here is an ALMA image showing the extent of the CO profile of this disk. You can see it extends out to about 4 arc seconds in radius. And if you look in the SPHERE image, you can see all these background stars that you're actually seeing through the disk. And again, their locations are plotted over here in these black circles. And so what we're planning on doing for these observations is do coronagraphic observations with NIRCam and look at this disk in a few filters, both in and out of sort of the 3 micron ice absorption profile. And so we'd really be able to detect ice in 2 different ways from these observations. The first is through we'd be able to map out across the entire surface of this large disk the water ice profile that we'd see from scattered light. So, right, you'd scatter off the water in the surface and be able to see that, as is done with a few disks before. But also at every location where there's a background star, we'd also be able to see the ice profile, this time in absorption. And so the absorption would actually probe the entire column density of water ice through the disk. So you'd try to get both the entire profile, the entire column, as well as just ice closer to the surface, and try to get a much better sense of both the vertical and radial distribution of ice in this disk. So we're very much looking forward to those data. So I'm going to touch now on some future directions I'm thinking of taking this modeling work. So given the sample of upcoming disk measurements, I think there's some additional parameters that would be great to explore in these observations. So I'd like to explore the effect of the observable ice features due to the disk mass, size, and especially the vertical structure. Also the grain sizes. This has an impact on which wavelengths are efficiently scattered. So it can, if we increase the size of the small dust grain populations, then that part of the disk that's dominated by scattered light can extend to longer wavelengths. Conversely, for smaller grain sizes, that scattering region will be restricted to shorter wavelengths. So I'm interested to see how that plays out in the features. Also, the stellar type. Some previous chemical models have shown that Herbig stars, more massive stars, can heat their disks much more, as you'd expect, and actually those disks can be relatively ice-free. But I think there's also been a lot of work showing that disk properties, like the disk mass and the disk size, tend to correlate with stellar type. So I'd like to, kind of include those correlations in the models as we vary stellar type. Also explored the effect of the external radiation field and the external cosmic ray field strength on the disks and their chemistry and how that might change their observable ice properties. One of the limitations of this model is that the model structure, the dust distribution, the temperature profile were fixed during the chemical evolution. And so potentially finding ways to incorporate effects like grain growth, vertical settling of the dust and radial drift, and couple those to the chemistry, I think would also be a step forward in this process, and see how those types of processes affect the observable ices. So I'll give you my summary. So motivated by the upcoming revolution in disk ice observations, we simulate observable ice features with a chemical evolution model plus radiative transfer. We find that water, CO2, and methanol ices are readily detectable in spatially integrated spectra of edge-on disks. We find that the CO, CH4, and NH3 ices are not easily detectable in the disk integrated spectra due to a combination of their concentration near the midplane, which is true for the CO and the CH4, their overall lower abundance than other species, which we found for CH4 and ammonia, and also their more intrinsically weak features, which is true for ammonia. The FAR, IR, H2O ice emission features are the most prominent from face-on disks. The CO2 ice features exhibit the greatest variation with the ongoing chemical evolution of the disks, whereas the methanol ice shows a striking difference between the inheritance and reset initial chemical conditions and makes a great discriminator between those two scenarios. We found that the spatially integrated spectra of edge-on disks are most sensitive to ices above the midplane, that's emphasizing the need for comprehensive chemical models to connect the observable ice reservoir to the unobservable ice reservoirs. Another way to get at this is through spatially resolved spectra of edge-on disks, as will be possible with JWST, and that can better probe the ices down closer to the midplane. And with that, I'll be happy to take any questions. And if you're watching this recorded and you have questions, feel free to send me an email.
All right, thank you so much, Nick. If you'd like to ask a question, you can either put it in the chat and I'll read it to the speaker, or you can use the raise hand feature. And I see that we have a question from Neil Turner, who says, could a molecular composition reset also be achieved through turbulent mixing between the cold interior and the warm UV and X-ray bright surface layers?
I think in principle, yes. So I think I didn't go into exactly how a reset would occur. I think, some of the general ideas of reset is that during the disk formation process, right, there's maybe the accretion of the envelope onto the disk can break up the molecules. But I think if there is a lot of mixture, yeah, that would make sense. Although, yes, I think that would make sense. Although it seems to me that maybe the observations so far are suggesting more of the opposite, where things are, sinking down to the midplane and potentially being sort of sequestered there, based on sort of the evidence from ALMA and the difficulty in finding all of the CO.
So playing off of that, so Neil says, cool method for simplifying the opacity distribution. How does the result depend on the number of k-mean clusters used in the grouping?
Yeah, I didn't go through, let me go back a little. I didn't go through the entire process to the end with different numbers of groupings, because the radiative transfer is actually incredibly time consuming for these edge on disk cases, where you're trying to track the photon packets that first have to be emitted from warm regions of the disk and then have to scatter at the right place with the right angles and then have to get out of the disk again and be absorbed. So I didn't try this and propagate in multiple ways. I did sort of explore, just sort of looking at these types of plots and cranking up and down the number of zones until I can kind of see by eye that it makes sense, that there are not vastly different regions of this parameter space that take on, the same, will be assigned the same average opacity.
All right.
But I do think, I do think that it's not that much work to add more zones. The k-means algorithm itself is quite fast. It does add time in later steps of doing the radiative transfer by having to put more stuff into it. But for instance, if we wanted to add more ice species, for instance, to this, I think that it shouldn't be a problem to increase the zone number, for instance, to try to make sure we're properly sampling all the distributions.
All right. So I have a question. First of all, I really love seeing someone use the Fogel et al. Code to study ices. Could you remind me what ionization rate, cosmic ray ionization rate you assumed in these models?
This was sort of the standard one, or Ilse's standard one, which is a little bit lower than, I guess some other standard ones. So I don't remember the exact number. I'd have to check again.
It's of order 10 to the minus 19 per second per H2.
Yeah. And so the idea is that, in interstellar space, it's usually maybe a couple orders of magnitude higher than that, but there's perhaps some evidence that, the sun and the solar system shield some cosmic rays from reaching, would have been our protoplanetary disk. So we tend to use this sort of the default now is a little bit lower.
I totally agree and do the same myself. Though I will say that having a higher ionization rate or having a more ionized disk, either from a higher ionization rate or a lower mass, will probably increase the amount of methanol ice that you're able to make, which will make the difference between the reset and the inheritance a little bit less clear. So I'm really glad to see that one of your next steps is looking at different ionization rates, because I think that's going to be really important.
Yeah.
All right, and then we have another question from Neil, who asks, why is torus used for the temperature structure, but then the similar RADMC code for the synthetic images?
Yeah, good question. This is just sort of a path-dependent approach to the methodology. The whole steps up through the chemical structure is sort of a well-established pipeline at this point in the methodology that people have been, like Ilse, like Dana, like Camber probably, have been using for a while now. And so this chemical code has been used to, explore a lot of different species, molecular species in the gas phase to interpret ALMA data. And so torus has been used historically for that reason. And the output files from torus are structured in a way as to be efficiently read into the chemical model. And so Ilse and Dana have that whole pipeline, this whole first half of the procedure as it's a well-oiled machine. So I picked up my sort of contribution with, okay, now what? What do we do with this list of abundances at different locations in time? And it's just that it's my personal experience I have with using RADMC and how to structure that with different opacities. That was my choice for using RADMC. But I don't think in principle that they should give particularly different results.
All right, and then we have a question from Vincat Manga in the chat, who has a question about the rate constants in the reaction database. Do the rate constants of various reactions have the effects of dust incorporated, e.g. heterogeneous nucleation kinetics?
I'm not sure exactly if they have heterogeneous nucleation kinetics. I don't exactly know what that means. I don't think so, if I understand that question properly. Again, the chemical code is mostly been designed up until this point to interpret ALMA data, right? That has been its primary usage, I would say. Theoretical work and with an eye on the the gas tracers. So there are a lot of reactions that are on the dust grains, of course, but I think some of the more newer and detailed work on exactly how reactions occur on grain surfaces, I don't think have been incorporated in the code yet. But your exact question, I'm not exactly sure.
All right, thank you. So I have another question about the chemical network. So I believe that the most complicated ice phase chemistry is pretty much methanol. Are there any plans to include more complicated formation of ice phase species in the future and see how that would impact your spectra?
Yeah, that is on our list to do. I think as long as we can understand the process from our sort of a rate coefficient modeling perspective, we're happy to throw it into the network and explore its effect. I know that there are a lot of very, very detailed work on grain surface chemistry using techniques that are much more complicated than can be maybe directly incorporated into a kinetics-based approach without a lot of work. So I think exploring how to do that is definitely probably something on our to-do list, but it's not always so straightforward.
Yeah. All right. So Alaria asks, or first says, very nice talk and results. Can you elaborate on why methanol is difficult to form in the disk alone in your reset scenario?
Yeah. So this is, let's see. Yeah. I haven't, let's see, go back. Yeah. What I would have to do to answer that question is and this is possible, but to go into the chemical code in more detail. And what's possible is you can look at any point in the model at any given time and see what are the dominant reactions that are happening. And so what I'd want to do is check, methanol is usually formed on dust grains, right? It takes CO, right, and then it adds hydrogens to it on dust grains, and then it comes off. So what I would have to see, my guess is that we know there's CO, so we have that ingredient, but there might just not be. It might be a problem with having enough free hydrogens to add to that. Would be my guess.
All right. We have another question from Neil, who says, in V4046 SAG, how much of the water feature towards a background star would come from the star's absorption modified light, and how much from the scattered light of the disk hosting star? Does determining the ice's abundances require decomposing the band profile?
Okay, so the first question is, I think, exactly what we're looking to do. So, right, we should be able to, look everywhere where there's not a background star, in every resolution element of the disk where there's not a background star, and map out the ice from the scattered light, and then compare that with where there is a background star and see how much deeper the feature is from the absorption. And that's the whole point of the proposal, is to try to figure out that difference. The question about mapping the feature in more detail, the structure of the feature. So the exact structure of the feature will be slightly different between scattering and absorption. So if we had, for instance, more spectral resolution, you might be able to, you can see that the scattered light feature is shifted to slightly shorter wavelengths and it has a slightly different profile than the absorption feature. So that's part of it. There's also other things, other species have features sort of around that 3 micron feature that can contribute to its exact shape. But I think, most of the, sort of the bulk of the feature is coming from water. So I don't think that there's really any issue with, for instance, misinterpreting the feature to be something other than water.
All right. Neil says, thank you for a very interesting talk. Are there any final questions for Nick? Youngmin?
Hi, Nick. Thanks for great talk.
Hi, Youngmin.
Hey, I have a question about the calculating opacity. And in your talk, you didn't say about how you really incorporated silicates and the carbonaceous material, but you're mostly working on the ices. So I was wondering whether those carbonaceous materials and the silicate materials contributing to your opacity here, and if it did, how you calculate it. If it doesn't, why is that?
Yeah, it does. Let me go back to this. So yeah, we have the specified distribution of dust, and that in and of itself is a mixture of 80% silicates and 20% carbonaceous material. And so we know what the dust distribution is everywhere, and then we take the results of the chemical model and we know the ice is everywhere. And so we find the volume fraction at every cell of all 6 of our ices as well as dust. And so if you look at this plot, one of these panels has dust as its axis. So we are mixing in dust the same way that we mix together the ices. So all sort of 7 of these species get conglomerated together in the model with various different volume fractions.
Thanks. One more question about that. So how do you determine the mixture ratio? Because now if you include the silicates and the carbonaceous and include some of the molecular species there, the parameter space probably so enormous to really determine their uniqueness.
So you mean like how do we get at these different volume fractions?
Exactly.
Yeah, so this is what, the dust is specified based on our parameterized disk model. So we already know how much dust there is and where it is. The ices, how much there are and where they are, that comes out of the chemical model. So we start with some very basic setup of putting in ice, but it's uniform spatially, right? You just say, or actually we put in most things in the vapor phase in the start of the chemical model. And the chemical model runs and it makes ices and it destroys ices and it does chemical reactions and it puts things on and off of grains and it does all the chemistry. And the output of that tells us how much ice there is everywhere. And so we look at every point in the model when that's done, and we know, okay, we have this much of each of these ice species at this point in the model, and we know how much dust there is there. And so we say, okay, for a grain at this point, what's its volume fraction of different ice species and of dust? And that varies, of course, spatially throughout the disk, which is why we have to try to account for that with this sort of grouping algorithm. Does that make sense?
Yeah, I understood. So the ice structures are layered or they're just mixed all together?
No, in our model we don't do a layered structure. So we mix the optical constants of the different constituent species with the Brugmann mixing rule, which sort of implicitly assumes that they're sort of an intimate mixture of the various constituents. I think that there can be a longer discussion about how realistic that is in disks. I think that in more quiescent phases, like molecular clouds, I think layered structures, there's a lot of evidence for layered structures. I think in disks, it might be a little bit more complicated based on the fact that you have small grains coated in dust, and then those are growing by sticking together and growing so all of their sort of individual layered structures can get sort of mashed together, and then things are also fragmenting and regrowing. So yeah, we use a sort of an intimate mixture just because it's the simplest way, and it would be very difficult to track the layering of ices throughout the chemistry model. But I'm also not sure it's entirely wrong.
Thank you very much.
All right. Any final questions for Nick? From Yvonne Pendleton says, great talk, thank you. Do you ever see a point where methanol ice is present but water is not? I ask because the Arrokoth findings from the New Horizon mission, Arrokoth at 45 AU, is thought to be quite pristine, and there was methanol but little or no water present, at least on the surface.
I would be very surprised. Water ice, so in all of the protostars, molecular clouds, water is the easiest thing to see. So we've seen that a lot already. And in, as I mentioned at the beginning of the talk, in the few disks where ices have been observed, water is the easiest thing to see and is the first thing to see. The 3-micron feature, the far IR emission features. I think there hasn't been any disk or protostar that I know of that has ices seen that does not have any water. In fact, almost all of those ratios that I showed at the beginning were all these other species with respect to water, right? So water is almost like the background in terms of how it's measured.
All right. We are going to stop there. I would like to encourage people to unmute and thank Nick for a very cool talk. Thanks, Nick.
Thank you.
Thank you, Nick.